projects is going to be assisted by an assistant. We have Brian Kate, who is going to be helping with the exercises in Brian Conrad's notes. So Brian, Semet Dasgupta, who's helping with title doc projects. Maybe stand up. Ralph Derkman, who's working with Clay Hedgie with my Sacred project. There. And Michael Temkins with is no food and drink allowed in you spill in expensive work. So. All right. Videographers are ready? All right. So without further ado, Brian Conrad.
Okay. So aim in my first two lectures this morning is to try to explain enough about the basic notions and initial theorems in the subject so that everybody else can kind of build on that and we all kind of have some common base of knowledge to go forward. The framework we're going to be considering is trying to develop some kind of sense of analytic geometry over non-archimedean. The field will always be denoted little k, the valuation ring will be R, and the residue field, which won't come up that often today, will be called k tilde. All right, and I guess this will just be the set of. Now, a crucial fact you might have in the back of your mind that we maybe build some finite extension of QP, but for technical and other reasons, it is convenient to allow infinite degree extensions, fields like CP, whose absolute value is not discretely valued. And to that end, since we are going to be considering finite extensions or higher degree extensions of K everywhere, or in many places, should in fact buddy for finite extensions of QP, but is in fact crucial. Is a unique absolute value that extends the one on K. Finite extension of K, it also has a canonical structure of non-Archimedean field, and since these agree on finite extensions, it even goes up to any algebraic extension just by patching these absolute values on all the finite subextensions. And in particular, you can go all the way up to an algebraic closure. Example. Caps. This is Q. That is usually denoted C. Its completed algebraic closure is kind of like the analog of passing to the complex numbers. That said, try to create this theory of analytic geometry, which is some kind of weird hybrid of analytic thinking over C and sort of algebraic schemes over general fields. And so to that end, we have to introduce the analog of polynomial rings. The replacement for polynomial rings, the building blocks for algebraic geometry over a field, sort of affine space and suitable closed subsets of that. And for us, the analog will be of that. But to build the right spaces, introduce the correct ring. Then variables over K denoted Tn or T small power series. So I'll just use multi-index notation. closed disk over K for X goes to the Tate algebra. Give its interpretation of defined to be the max coefficient. So if f is some max aj, so if f is j x to the a, and since these guys go to 0, there is certainly some multi-index with a max, and we'll call that. This notion of magnitude on think f is some kind of a function on the closed unit disk. A fundamental difference between the kinds of geometric objects we're going to be considering and the kinds that you may have seen if you've studied maybe p-adic analytic manifolds in a more classical setting is that, as with algebraic schemes over a field, there will be many non-rational points. I mean, unless the base field is algebraically closed. So, for example, we'll see that an analytic space over QP, in the sense we're going to study, will not just consist of QP rational points. And so when I talk about the closed unit disk, for now, you might want to think about just the n copies of the n-fold product of the valuation ring of K. But we'll later see that we really want to, in some sense, consider all the finite extensions of K simultaneously and to somehow mod out by some kind of Galois action. And anyway, in order to define the correct space, we need to better understand a little bit more about the structure of this ring. So let me record some properties of this norm on this algebra. So why should I call it a norm? So let me just list some properties of this thing. Well, obviously, it vanishes only when f is 0. A little bit more interesting is, all right, well, when I scale by something, scalars pop out. That's sort of from the definition. Well, actually, first we'll say another obvious one. It's non-archimedean. Right? If you put in two guys, it's bounded above by the max of the norms of the two pieces, simply just by. A little bit less is it's actually multiplicative. And submultiplicative is easy. This equality requires a little bit more thought. That's left as size. And so this way of measuring the magnitude of elements is going to be very helpful in getting our hands on the. Now, we want to think about this ring as being something like the replacement of a polynomial ring. And so to that end, let's think a little bit about the ways that we can map this ring back into. As we think about affine space, somehow the points of affine space we think of as maps from the polynomial ring into a field, maybe the base field, maybe a finite extension of the base field. And so let's see this Tate algebra has lots of interesting maximal ideals. So let's think about maximal ideals of Tate algebra. So before choice of. So, well, one thing we can do is, if I give you any n tuple of elements in the valuation ring, you can just send any power series. Okay? And so this is basically determined by the condition xj goes to cj, and this evaluation is easily checked with respect to these certainly a bunch of modulo these kernels of these maps. These are surjections K. But in no reason to restrict ourselves to just K. In fact, for any finite extension of K, or evaluation map, maybe I'll call this evaluation map P, and any n tuple of elements in the evaluation ring, we get an evaluation map K prime, sending the xj's to these equations uniquely determined by this condition together with continuity. in general, this may not be surjective, but we could choose a bunch of Cj primes, at least enough of them, to generate this extension. See that there are lots, so the upshot is that there are lots of maximal ideals with Tn mod m equal to k prime. Okay? So to the extent k has lots of finite extensions, we have lots of these sort of maximal ideals that in some sense don't correspond to rational points. This is much like thinking about a scheme over a field as opposed to just the classical Euclidean space over that field. Okay, so we're gonna just see later that in fact, in a certain sense, these are all of the maximal ideals. So this Tate algebra will have many properties that are in some sense reminiscent of familiar properties of polynomial rings over a field that are sort of what you need to sort of get algebraic geometry off the ground. And so what I want to do is record without proof. I'll say maybe an infinitesimal amount about what you have to do to make the proofs. I want to record some of the properties of this Tate algebra, and you should keep in mind the analogies with the polynomial ring, and we'll see that starting with these basic properties, we'll really be able to do quite a lot with the rings and the spaces that we'll build out of this Tate algebra. Okay, so let me just record some of these properties. I apologize. I wish there was another screen because I keep sort of pulling these off, and then anyway, you all have these typed notes. You shouldn't be taking any notes because it's all there. Anyway, well, you can do whatever you want. Okay, so properties of this Tate algebra. Well, first of all, I mean, it's defined as a subgroup of Power series, so it's obviously a domain. But not quite as evident is, so this guy is actually, it's Noetherian. So that's nice. It's regular. That's good. In fact, it's a unique factorization domain. And for geometrical purposes, it's very good that all the maximal ideals have height n. Okay? So it's very similar to the case like with residue class field. So if I mod out by any maximal ideal m, this is always a finite extension of k. So that's quite nice. Max spec, right? When you classical algebraic geometry gets quite far with max spec, the moment you go to more general rings, it kind of dies because max spec isn't functorial for general rings. But for these guys, it actually is. And well, we'll see that will sort of come out of some of these properties. To get by with max spec, another important property is that Tn is what's called a Jacobson ring. Every prime ideal is the intersection of the maximals over it, or put another way, you can determine you can determine whether something is nilpotent just by checking if it vanishes, for example, at all of the maximal ideals. Okay, so one consequence, so this says P is the intersection of M over P for all primes P. And so one consequence of this is that if I is an ideal, then A in Tn mod I is nilpotent. Well, it's nilpotent only if and only if it lies in all the primes over I, but every prime is the intersection of the maximals over it, so it's nilpotent if and only if A lies in M for all M containing I. Of course, Gothic German M is my convention notation for a maximal ideal. Okay? So we can detect nilpotence just by studying the space. If we're going to be with this Gauss norm, oh goodness, I forgot to mention, the Gauss norm, for definition, this kind of max absolute value, it's very easy to a T called a Banach space, or more generally what's called a K-Banach algebra, to the Gauss norm. So meaning the Gauss norm, well, we recorded that it was a norm, but it really is complete with the Banach space, and it interacts well with the multiplicative structure. In general, Banach algebra, the norm is only required to be submultiplicative. The norm of a product should be bounded above by the product of the norms. The Tate algebra is has this kind of extra feature that's exactly multiplicative on the. In any event, this is a Banach algebra, and that's going to be very important for various operations that we perform with this ring. And in order to have that interact well with the commutative algebra properties of this ring, it's record the fact that every ideal in this Noetherian ring, every ideal I in Tn is automatically closed for this topology. So in some sense, it's very reminiscent of if you think about complete local Noetherian rings, where every ideal is closed for the max adic topology. But this topology is not defined by commutative algebra. It's defined by this sort of norm structure on the field. So although you might think that some of these topology properties are similar to some things that you've seen in the study of kind of finite modules over complete rings in commutative algebra, it's not really an instance of the same phenomenon, because So these are the basic properties. Give you a geometrical interpretation of the Gauss norm, which is going to explain its Gauss norm. So I studied the theory of Gelfand's. What is it called? This Gelfand transform. Right? There's this sort of relationship between compact topological spaces and their spaces of continuous complex valued functions, and there's a nice relationship. Although if you don't know what I just ignore it. So the geometric is this, that if I give in the Tate algebra ideals. So take a maximal ideal. I'll denote it x for psychological purposes. We think about it, although I might also denote it m sub x if I feel like it. Now, for every point x, I'll write kx. This is just shorthand. Kx is Tn mod the maximal ideal. This is a finite extension. And if I give you any element f in Tn, I'll write f of x for its image in here. This is f mod mx. Okay? Well, this is a finite extension of k, so it has, as I said at the beginning, it has a unique absolute value extending to 1 on k, so we can take that absolute value. Okay? So we sort of have this space of points, and you want to think about this as being like the union of all the closed unit disks over all the finite extensions of k at once. All right? However, we're only recording the kernel of the map, not the actual map of coordinates itself. So if you have two n-tuples of points that are Galois conjugate, the evaluation maps have the same kernel, so they're really the same point in this space. So set theoretically, what the space is the closed unit n disk over k bar modulo the action of the automorphism group of k bar over k. Just a space of maximum. At each point, we have this absolute value of, and the suprema. Often, this is an instance of the modulus principle. And this is a very interesting fact. It's going to be incredibly useful in a more generalized form. And one thing it's very suggestive of is the idea that you'd like to think about this closed unit disk as if it were a compact space. But it's not really a compact space. Even if k is qp, this thing has points valued in all finite extensions. So this is acted under any standard topology. This is sort of suggestive of that idea. Useful. So that's sort of the story of the Tate algebra. But of course, to get anywhere, we really want to work not with the closed unit disk itself, but with loci that are cut out inside of it by analytic equations. And so we introduce a class of rings that are going to be the aphanoid algebras. And these are going to be the analogs of general finitely generated algebras over a field, which are the true building blocks. Well, Tate algebra. Maybe you've all read the notes and everything I'm saying is known to everybody. I don't know. No, any questions? No. Okay. We'll get as a bonus. But A, so it's a K-algebra, which has a presentation as a quotient. So we this x1, xn, modulo ideal. Of course, there's no canonical presentation, so this is not really part of, this is just some way of describing it. And definition A, in terms of this presentation, we have to pay attention to different choices of the presentation. One thing to observe, though, I recorded before, every ideal when you have a Banach space over C or R, and you have a closed subspace, then the quotient space has a natural Banach norm. Namely, for every vector in the quotient, you take the infimum of the norms of its representatives, and that defines a nice Banach space structure. Over a non-Archimedean field, the definition of a Banach space is exactly parallel to the complex case. You have a norm compatible with the absolute value on the scalars, and it should be complete. And of course, as with the field itself, in a non-Archimedean setting, when I say Banach space, we require the triangle inequality to hold in the non-Archimedean sense. The norm of a sum of two vectors is bounded above by the max of the norms of the two pieces. Okay? And thing is, in fact, Banach with respect to residue norm. By residue norm, I just mean, given such a presentation, we take the norm of an element to be the infimum of the norms of its representatives. Okay? And so that really gives us the structure of a K-Banach algebra. One little wrinkle is, in the general definition of a Banach algebra, let me remind you, the condition is that the norm of a product is bounded above by the product of the norms. Okay? There's no reason, if something is a product in here, why the representatives for A1, A2, when you minimize this, it has to be well related to the ones for A1 and A2 separately. So at best, you just have an inequality. All right? And in general, you can't expect the equality that you have in the case of the Gauss norm. Okay. Anyway, so this has a K-Banach algebra structure. It's not a priori evident that if you chose a different presentation, that the other Banach structure, the norms are probably different. Are the topologies the same? It's not immediately clear. Okay. So that said, let me just mention properties of affinities in general that are immediate consequences of the case of algebras. For example, well, every maximal ideal of this is just a maximal ideal of Tn that contains I. So, for example, all the residue fields at the maximal ideals are finite extensions. All right? All, these rings are Noetherian, they're Jacobson, and so forth. Probably not regular. Local ring complicated. And then you inherit the nice residue field property of finite integrated algebras over a field. It's bonus. Now that we have a large ring to work with, we can think about some functorial constraints. So if A is calculated, for the ideals of A. Okay? So for example, if I give you x in M of A, we define K of x to be A modulo that maximal ideal. This is finite over K. And A in A is nilpotent if and only if it vanishes in Kx for all x in M of A. Right? Simply because this just says that A lies in every, if we think about this as a quotient of a Tate algebra, the condition of vanishing in the residue field says that you lie in every maximal ideal over the defining ideal of this guy as a quotient of the Tate algebra, and therefore you lie in the nil radical of that, which is to say that you're nilpotent in the quotient ring. Okay? So this sort of familiar feature from algebraic geometry isn't that we can define this space for any ring, that if I give you a map, if this is a K-algebra map, is a K-algebra map of affinoid algebras, then you get, by pullback, a natural map backwards on max spec. Okay, given any m, you look at the pre-image. Okay? Of course, one has to prove that this is actually a maximal ideal and not just a prime ideal. So that's just left as one of the exercises, but the proof is exactly the same as when you did this exercise when you were first studying algebraic geometry. Now that said, let's give some interpretation, geometrical interpretation. What is this space? Well, I sort of alluded to it before. If we think about A, so the geometric meaning, A of algebra, A, then M of A, well, these are maximal ideals. Let's say I here is generated by F1 through FR. Well, M of A, we want to think about this, well, these are the maximal ideals of Tn. So you think about that as like a closed unit disk with the property that the ideal contains this ideal, meaning it contains these elements, so that F1 of x equals FR of x equals 0. Okay? Put another way, maybe a little more conceptually, we have Tn surjecting onto A, so therefore there's a pullback map. M of A goes back into M of Tn, and the image is exactly, this goes bijectively onto the space of points in this polydisk, at which all these defining relations actually vanish. Okay? So these are going to be the at least set theoretically, the basic objects to work with. But one complication is, in general, we don't want to work with topology on these spaces. Let me first describe what the sort of naive topology is on these spaces, and then we'll see that it isn't really so useful for geometrical purposes. And then to get the theory off the ground is going to be Tate's observation that we can, in some sense, restrict the class of open sets that we consider and actually get something which, in a more sophisticated way, retains connectedness that one wouldn't ordinarily have expected to have based on experience over totally disconnected fields. So to that, actually, let's how should I do this? Well, we'll come back to that in a little minute. I'm sorry. Let me just record some before we discuss that. Let me come back to some properties of affinoid algebras in general. Then we'll come back to the topology on these spaces. So the basic properties of these affinoid algebras, first of all, as I mentioned before, they do inherit some properties of Tn. They're Noetherian. They have a reasonably nice local dimension theory. But there's no analog of the Gauss norm. On the Tate algebra, there's a sort of obvious Gauss norm that's staring us in the face. And actually, I should point out, so if we come back to this formula, one nice feature of this formula for the Gauss norm is this formula is completely intrinsic to this ring. And in particular, even though the definition of the Gauss norm involved coordinates, the xi's, if you imagined applying an automorphism to the ring that might shuffle the coordinates around, like recenter the disk, for example, it doesn't change. Right? This side of the formula is completely intrinsic. So in fact, the Gauss norm is intrinsic to the ring. All right? It doesn't really depend on coordinates. You can't expect to be so lucky for more general affinoid algebras. So one very important property of affinoid algebras is that whatever k-Banach structure they may have, whether it comes from a Tate algebra presentation or not, they're all equivalent to each other. So k norms, k-Banach algebra structures on A are equivalent in the sense that each is bounded by a positive constant multiple of the other. So if we make topological statements that a sequence of elements is bounded, that a sequence is tending to 0, these properties are independent of the choice of the particular k-Banach algebra structure, so they're intrinsic properties of that sequence in the ring itself. And of course, in order for it to be useful, it's crucial that this Banach structure is in fact functorial. So, and this is also not at all obvious. You A prime to A, any map of k-aphenoids, it is automatically continuous. For what topology? Well, by part one, Banach norm you want to pick. They all define the same topology. Okay? So in the sense of bounded linear maps between Banach spaces, the norm of f of a prime is bounded above by a constant multiple of the norm of a prime by some universal constant upon the of k Banach norms. So that's quite nice for making various constructions that we'll see later. And there's also what's called the maximum modulus principle. So this is, for the Tate algebra, it's an easy exercise. For these more general ones, it requires more serious input. And that says that for any f in A, whoops, shouldn't call it f, sorry, for any A in A, if I contemplate, well, I'm going to call something the sup norm of A. I'm going to consider the supremum over all points in the maximal ideal space of the absolute value. It's not obvious necessarily that this is finite. In fact, it is finite, and in fact, the maximum is attained. Okay, so that's actually quite nice. Now, in general, you cannot expect this to be, in the Tate algebra case, this was in fact a Banach norm, but a Banach algebra structure. In general, you can't expect this. First of all, there's a silly reason, which is that if an element of A is nilpotent, well, then these are all going to be 0. So this usually isn't even a norm. Okay, this will kill all the nilpotents. But in fact, it's a nice fact, again, not at all obvious, that if this ring is reduced, this is in fact a k-Banach algebra structure. So if A is reduced, as the Tate algebra is, for example, this is a k-Banach algebra structure. I'm sorry, reduced meaning that there are no non-zero nilpotents, so all nilpotents are 0. Well, the only nilpotent is 0. Okay, so in general, there's no canonical norm. In the reduced case, there is this one, but that doesn't mean you necessarily want to focus on it too much. But anyway, this again supports the sort of vague idea, which can be in some sense made precise with more sophisticated approaches, that the space of maximal ideals should be thought of as sort of being like a compact topological space. Okay, so these are three of the basic properties of the Tate. I should just mention in passing that one does have analogs of other more commutative algebra properties. So, for example, there's an analog of the Noether normalization theorem, that if this guy has dimension D, it can be expressed as a modular finite extension of a D-variable Tate algebra. All right? And in particular, if this is a domain, all of its maximal ideals will then necessarily have local ring of dimension exactly D. Okay? So there is, so I'll just mention this in passing, that one does have an analog of the Noether normalization theorem as well. And maybe I'll just mention one last property, which is that every afinite algebra, by which I mean an algebra which is finite as a module, is necessarily k-aphenoid. Okay, so that said, so these are the in some sense the basic properties of Tate algebras of aphenoid algebras, but we the canonical topology. So we can think about this as a set of, when we look at maps from A to K bar, maps over K with image in a finite extension. Modulo the action of the automorphism group of K bar over K. This is a geometrical way of interpreting the meaning of points of the maximal ideal space, because a maximal ideal gives you a finite extension which up to automorphisms of such n-tuples. Now, this set upstairs, this has a natural topology, okay? Because we can think about this as topologizing by closeness of coordinates. If we choose a presentation from a Tate algebra, think about the way you define the topology directly on the closed unit polydisk over any particular field. So this is a very natural Hausdorff topology, and then we just consider the quotient topology on this. Okay? And with the quotient topology, so we'll just use the quotient topology. And again, concretely, if you view A as a quotient of a Tate algebra, the choice of the presentation doesn't actually matter if we want to parameterize this by n tuples and K bar modulo this action. If you use the quotient topology, so it's one of the exercises that this is a totally disconnected Hausdorff space. This is the replacement of the naive notion of a p-adic analytic manifold. But again, I have to emphasize that there are points of this space, unless K is algebraically closed, there are points of this space whose coordinates, with respect to, let's say, a presentation, are not all in K. All right? So it's not just a matter of working with a standard unit polydisk. You have to put them all together and mod out. But nonetheless, you do have a natural, totally disconnected Hausdorff space that you can associate to any of these rings. But the whole point is this. Yeah? So geometrically, these spaces with this topology are not necessarily the most useful things to study from a geometric point of view. Okay? So in the next lecture, we're going to sort of take up Tate's discovery of how to, in some sense, get around this problem. Roughly speaking, we're going to restrict the class of open sets that we allow ourselves to consider, and we're also going to restrict the class of coverings of those open sets that we allow ourselves to consider. And by restricting in a sufficiently intelligent way, we will in fact we will obtain, in some sense, nice topological properties on these spaces. Okay? So at the outset, these spaces do have a natural topology, but the whole point is going to be to somehow refine it, replace it with something that's much, much better, much easier to work with. So that said, if we're going to want to do more sophisticated constructions with these affinoid algebras, it's very useful to record that within the category of all the affinoid algebras, what is it that makes the Tate algebra so special? Okay? Well, if we go back to algebraic geometry land, what is it that makes, if you think about algebras over a field, or schemes over a field for that matter, what is it that makes polynomial ring and n variables so special? What is its universal property? Okay? Affine n space, is the universal space equipped with an ordered n-tuple of global functions. To give a map to affine space is exactly to give an n-tuple of functions. And so to that end, I want to record a similar property for the Tate algebra within the context of affinoid algebras. So let's record that. So what's the universal property of the Tate algebra? And of course, once we get a geometric theory, so far these maximal ideal spaces are just sets. Well, we gave them a topology, but it's not going to be the right one. They don't really have a good, rich analytic structure yet. But this algebraic universal property that we'll formulate now will later turn into a geometric universal property of a kind of a closed unit disk, once we give the max space of Tn some more hefty analytic geometry structure. So what's the universal property? Well, let's see. Let's say I have a map from Tn to script A, which is just a k-affinoid algebra. Or if you like, even a k-Banach algebra. Okay? And say you require this to be a continuous map, which in this case is automatic. In this case, it's a condition. So let's consider a continuous map, and let's see where the xj's go. The xj's go to some elements aj in here. Okay? Well, the thing is, these xj's, they're bounded for the norm in here, but they're better than that if we look at their powers, right? Let's say using the Gauss norm. All the powers of these elements also have Gauss norm 1. Right? These elements are what are called power bounded. Power bounded means that the sequence of powers is bound. I shouldn't use n here, I'll say m. Is bounded. If I give you an element in a Banach algebra, I'll say that it's power bounded if its sequence of powers is a bounded sequence. Notice if I replace the norm with an equivalent norm, this property doesn't change. So in any k-affinoid algebra, the property that an element is power bounded is in fact an intrinsic property independent of the choice of k-Banach algebra norm, because any two such norms are bounded above by a positive constant multiple of each other. And in fact, now that I've just mentioned it, before we come back to the universal property, let me just say that for k-affinoid A, power bounded is equivalent to the condition that the sup norm is at most 1. Okay, so there's a convenient criterion to detect when this happens. In any event, these guys are power bounded. If I give you a continuous map of, well, Banach algebras, and in particular Banach spaces, bounded sequence goes to a bounded sequence, right? Because the norms are, bounded above by a constant multiple of the other one. So therefore, these elements must be power bounded. So thus, just by continuity, each aj must lie in what I'll call script A0, which is the set of power bounded elements of A. Okay? And, well, this is certainly not a K subalgebra, because if you multiply, for example, in the p-adic case, I mean, the elements outside the valuation ring aren't in here, right? You raise into powers, their absolute values grow and grow and grow. So this is, in fact, an R subalgebra. Thanks to the non-archimedean inequality, if you add two power-bounded things, it's still power-bounded. Okay? So this is, in fact, a nice R subalgebra. And so we see that any map from a Tate algebra to an affinoid, or more generally continuous map to a k-Banach algebra, must carry the xj's to power-bounded elements. On the other hand, this uniquely determines everything by continuity, because, well, every element in here is a limit of polynomials, and so by continuity it's determined by what we've done here. But the important point is, conversely, if I want to send the xj's to power-bounded elements, any convergent sequence in the xj's with coefficients tending to 0 makes sense to form in this ring by plugging in the aj's for that. So notice if I give you some f equals summation cj xj in the Tate algebra, then summation cj, I'll just write a to the j, makes sense for all a1, an that are n tuples in the Euclidean space on the power-bounded elements. And this is the universal property, that given any n tuple of power-bounded elements, there does exist a unique continuous map satisfying this condition. Okay? And so this is very similar to the universal mapping property of polynomial rings. So this is the universal property of the Tate algebra. Right? So in particular, for our purposes, given an affinoid algebra, to give a map from a Tate algebra to an affinoid algebra is equivalent to giving an n tuple of power-bounded elements. That's where the x's go, and every series in the x's with coefficients tending to 0 just gets sent by evaluating at those points. This makes sense in this Banach space precisely because these guys are all bounded, and these guys are going to 0, so by completeness, this thing actually makes sense. Okay? So that's the universal property of the Tate algebra. Okay, so that's probably enough for the first lecture. Let me just see if I hit everything that I wanted to say. Yeah, I think that was quite adequate. Okay, so as I said, in the next lecture, what we're going to do is, this is in some sense more algebraic than geometric. we've introduced a topology on the space of maximal ideals, and it is Hausdorff, but it has this total disconnectedness problem. And so what we're going to do is introduce a very interesting class of subsets of the maximal ideal space, a class of open sets for this canonical topology, and we'll see that if we only work with these special kinds of open subsets and special kinds of coverings by them, that we will severely restrict what kinds of separations we can make in the space, and we will recover something more in the spirit of a connected topology, as is more familiar from the case of analytic geometry over the complex numbers. Okay, so I'll stop there.
So are there any questions?
Yes?
Why is it called the Gauss norm?
All right, so the question is, why is it called the Gauss norm? Where's Tate? Maybe it's because it has something to do with Gauss's lemma, maybe? Oh, right, yeah, okay, very good, yeah. So if you go to the exercise to prove that the Gauss norm is multiplicative, you have to do something that's very similar to the proof of Gauss's lemma. Yeah, there you go. Is primitive, right, the product of primitive polynomials is primitive, and this sort of the analog of that is what makes it be multiplicative. Yeah. Okay. So yeah. So one could ask. So the question is, if I give you the sup norm is some kind of canonical one, does it come from a Tate algebra presentation? More generally, you could ask, if I give you just an abstract K-Banach algebra norm, can you cook up a Tate algebra presentation for which that is the residue norm? And I don't remember I think the answer is negative in general. There are some funny examples in the BGR book that I don't recall offhand. Michael, do you remember offhand? So this is addressed in some places in the BGR book. They talk about whether something may or may not be a residue norm. So there is an wait. So certainly in the discretely valued case, there is an obstruction. You see that the Tate algebra has the property that the norm of every element is, in fact, the absolute value of something from the field. Right? So if you use the Gauss norm, the only numbers that you'll get out are, in fact, in the value group of the field. And so at least in the discretely valued case, if you take the infimum of such things, well, as long as your value group is discrete, the infimum of elements in the value group is, again, in the value group. So if you're working over QP, any norm coming as a quotient of the Tate algebra, its image has to still just be powers of P. But we'll see in the next lecture that one can get norms which have elements way outside the value group of the field. So there is an obstruction. Yeah. Yeah. Right, yeah. So yes, so a norm is called... Right. Right, okay. So in general, you call a Banach algebra norm distinguished if it does come from such a presentation. And so in the BGR book, they do show that over an algebraically closed field, they all arise this way. And in general, there are obstructions to this, but yeah, there's a theory of these norms. You're asking what is the general obstruction? Right. 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 No. But I mean, in general, yeah, no.
Okay, well, let's make it again.
When are we reconvening? Let's reconvene at 10:05.
Yeah, so exceptionally, since Ryan is giving 2 talks in a row,